So I would like to start by thanking the organizers for organizing this conference and for giving me the opportunity to speak. This is, I think, the second time I stepped into this building. Last time was 30 years ago. So I'm happy to be back and to see that nothing has changed, except that for the creation of a new institute, which I hope will change the place enormously. So my talk is called Magnificent Four with Colors and Beyond 11 Dimensions. And so I hope it will be a technically much simpler talk than the previous one, because I decided to leave out all the technical details. But if you're interested in details, you can ask me later. So the talk will be mostly about counting boxes in various configurations. Now, why do we want to count boxes? Well, that's because a popular approach to quantum gravity, at least it was popular 30 years ago when I first stepped into this building, was to approximate space-time geometry by some discrete structures and then try to set up tools for summing over these discrete structures and then hope for some kind of continuous limit which will look like semi-classical gravity, maybe with some quantum corrections. So one success story in that fashion, in that field, was that of two-dimensional quantum gravity, where the two-dimensional random geometries could be built out of, let's say, small triangles, and then enumeration of triangulated Riemann surfaces can be cast in the form of the fat graph expansion or 't Hooft expansion of a large n matrix integral. And so you can compute more or less everything about matrix integrals, and so you can compute more or less everything about two-dimensional quantum gravity. And so that was the story which was first very exciting for physicists, and then it was picked up by mathematicians who are excited about this to this day. Every 4 or 8 years, in other fields, medal goes into this field, and so it's very interesting. Connects to all kinds of geometries from classical mathematics and from conformal field theory as well. So in that story, so you study the integrals of the matrices of size n by n, let's say, and as n goes to infinity, if you re-expand the free energy in inverse powers of n, you can actually see your eyes the contributions of genus G Riemann surfaces. So in 2 dimensions, if we talk about oriented Riemann surfaces, we have essentially one parameter which governs the topology, the genus or the order characteristics, 2 minus 2g, and that's the organizing principle for this expansion. If we go up in dimensions, that actually turns out to be difficult. So one obvious generalization of a matrix model, which would produce now 3-dimensional geometries out of some simple blocks, would be to do the tensor theory, where the elementary fields would be not just matrices with 2 indices, but some three index structures. Now, unfortunately, for general 3 manifolds, there is no analog of genus. The order characteristics vanishes for any compact 3 manifold. So there are, of course, topological invariants of 3 manifolds, but there are too many of those, and they're not organized as a number, or maybe a simple set of numbers which you could use to expand things. Nevertheless, in recent years, people have rediscovered, let's say, these tensor models in connection of this to the so-called SYK model, where some kind of expansion in topologies of 3 manifolds seems to be taking place, but what is this main topological characteristic of 3 manifold is not really understood. It's from the tensor theory point of view, this is a so-called Grau index, and it is some kind of souped-up version of a genus of a Riemann surface. But as far as I know, there is no intrinsic definition of that from in three-dimensional topology. So in this talk, I will discuss two models of random three-dimensional geometries. In fact, one model will reduce to another one. I will not claim that they actually quantize three-dimensional Einstein gravity, but I claim that they're nevertheless interesting because they will probably teach us something about the 11-dimensional supergravity. So, and even beyond. So one way to generate random geometry in d dimensions is to study the growth models in d+1 dimensions. So you build your random structure by some simple rules, local simple rules, starting with the trivial one and then adding blocks. So, and actually, so my slogan here will be the geometries from partitions. So the structures which I will be enumerating, which will represent this random geometries, will be partitions of various kinds. So the simplest problem which we all do in kindergarten is just counting, and that has no real structure. So we just enumerate, as Mayakovsky did, we enumerate cigarette butts or steam engines. So some objects without structure. We don't care what the structure of these objects is. Just count 1, 2, 3, and so on. And now we can actually start. The simplest way of adding a structure is to pay attention to what the object is built of. And so if all you have are numbers, then you can actually create already a structure here by looking into the ways a given integer can be partitioned into the sums of non-negative integers. So there's only one way to partition 1, it's just 1. But for 2, there are 2 ways. It's 2 or 1 plus 1. For 3, there are 3 ways, and so on. And then there is a famous Young diagram representation of these partitions. So it may appear that you have n ways of doing this for number n, but of course, this is not the case. You can think of these partitions as the simplest bound states of elementary objects being squares, and then you try to glue them. That problem actually arises in construction business. So if you take a kind of a gardening cart and a bunch of bricks and start throwing bricks so that they just fall and then slide down by the force of gravity. So if you just throw a pile of bricks one by one, what kind of picture you will get? Of course, you may get different things, but the probability of getting a different picture actually depends on number of ways of building that given partition, starting with the trivial one. And so there is a graph which describes interrelations between these pictures. So you start with this empty thing, and then you add 1 square, and then out of this you can go adding the square on the left or on the right. So there are you can move and so on. So you can move along this graph. And so let's say for this picture, there are 3 ways of arriving here, starting from here. So either this way or this way or this way. And so the probability of getting that diagram is 3 times bigger than the probability of getting this diagram. Maybe 50% higher. So to get here, there are 2 ways, and to get here, there are 3 ways, and so on. So that's from this you can go to a mathematical problem of investigating random Young diagrams, and that's sort of and slightly relates to the previous talk because the measure on a discrete set of Young diagrams which you get is called the Plancherel measure, because that's actually the Fourier transform over uniform measure on the symmetric group. The symmetric group representations are labeled by Young diagrams. And so if you start with the uniform measure on the group itself and Fourier transform it, then you'll get the measure on the set of representations, which will be proportional to the square of the dimension of the corresponding irreducible representation. So if you introduce a fugacity for the number of little squares, you get the measure on the set of all partitions. In the way I've written it, it's a normalized measure. So the sum over all partitions of this quantity is equal to 1. And for a given partition, so this measure knows something about the geometry of the Young diagram. One way to represent this number is to take a product over all squares. In this case, there are 4. You compute the Hooke length of the square, so the number of boxes which are to the left and to the right, plus 1, and product over all those boxes. So this box, for example, has Hooke length equal to 1. This box has Hooke length equals to 2. This box has Hooke length equals to 4. And this has Hooke length equals to 1. Remarkably, that trivial thing which you can encounter in brickwork is the simplest example of an instanton measure, which you get in doing the computations, the one-loop exact computations in n equals 2 supersymmetric gauge theory in 4 dimensions. So that, so if you have a solution of self-duality equations in 4 dimensions, and you evaluate the one-loop contribution by integrating out the fluctuations around its solution, for the suitably deformed gauge theory, the ratio of determinants, so I wrote here superdeterminant for the superangular theory, will exactly turn out to be this Planck measure. This is a slightly artificial gauge theory. It's a U1 gauge theory on non-cumulative spacetime. So it's a theory which has instantons, but there are no parameters, so these contributions are just pure numbers. Once you generalize to higher rank, that becomes more interesting. So this is the theory which has gauge fields, a couple of Weyl fermions, and a complex scalar. So that's for pure superangular theory. And the supersymmetry transformations are such that the instantons or anti-instantons are configurations which are preserving some fraction of supersymmetry. And so by expanding around these configurations, you can compute the path integral exactly, if your boundary conditions allow that. And so if you're doing the partition function, so you integrate out all fields, then the path integral will actually localize exactly to the integral over the modular space of instantons of varying charge. There is some instanton measure, which is that ratio of determinants which I depicted in the previous slide. And then if you further deform the theory by using the rotational symmetries of R4, by breaking the translational invariance, so that's a modification of the symmetry of the theory which makes it invariant under a non-standard supersymmetry. It's a non-Poincaré supersymmetry. Nevertheless, it has fermionic charges which square not to translations as in Poincaré supersymmetry, but to rotations. So it's a kind of ADS-like supersymmetry. So there, the supersymmetric field configurations are not just instantons, but they are instantons which are in addition invariant under the rotations. And so they actually, they don't have a modular space, they are isolated. And so that's why the partition function becomes a sum. Instead of an integral, it becomes actually a sum over special instanton configurations, which happen to be identified with partitions or antipoles of partitions for UN gauge theory. And this measure depends on the new parameters which are used in deforming the theory, which have the meaning of the angles of, or rather frequencies of 2 independent rotations of 4-dimensional spacetime. These are rotations in Euclidean version. If you do Lorentzian continuation, one of them will be again the rotation, but another one will be a boost. Yes?
What is the supersymmetry of?
So this is the, as I said, this is modified supersymmetry. It has 2 supercharges, and they the anticommutator is the infinitesimal rotation of space-time generated by this matrix. I'm not sure. It's a good question. It's no, it's not OSP because that would have the bosonic subgroup would be a product of orthogonal and symplectic group. Here the bosonic subgroup is it's a torus. It's U1 cross U1, maybe cross another U1, which is the remnant of the SU2R symmetry. So it is. So it's smaller. It's not a simple supergroup. So it's probably some split form. Now, if we forget about the origin of this model, just look at the supersymmetric gauge theory partition function, then the expression for the partition function becomes the sum of the random partitions, which are random piecewise linear geometries now. So here I'm drawing the picture for U3 gauge theory. So there are three corners of a piecewise linear function where I start my growth process. So here, sorry, let's do it slowly. So I start with empty picture, and then I started throwing in bricks. But now these bricks are allowed to land in either of the corners. And so then the general configuration would be a collection of, in this case, three Young diagrams, which are slightly squeezed so that they fit into this picture. And the probability of getting this particular configuration has a Boltzmann factor, which you can interpret as the Boltzmann factor of a gas, of a one-dimensional gas of particles. The particles being the corners of this green piecewise linear function, which is the boundary of this picture. And there is a two-body interaction kernel. Now these corners can be pointing north or pointing south, and they have a meaning of positive and negative charges. So this is a gas it's a plasma of one-dimensional charges, which have some log-like potential. So it's indeed like a Coulomb gas in the matrix model, except that here you have charges of both positive and negative charges. Now, if you remove the deformation from flat space supersymmetry, so go back to point covariant theory, then this measure actually happens to have an exponentially large behavior. There is a thermodynamic limit, effectively, in which the dominating geometry into this sum of random geometries is actually smooth. And so that's the simplest emergent geometry out of some discrete structure, which is, again, captured by some gauge theory. The novelty here is that this is not the matrix model, which was a zero-dimensional gauge theory, but it's a four-dimensional supersymmetric gauge theory.
So this is like a volume factor?
So this is like a volume factor. So this 1 over epsilon 1, epsilon 2 is like the volume of four-dimensional space-time. It's this deformation, which I was using, the so-called omega deformation, it's some kind of finite. It's effectively it imposes it places the instantons of gauge theory in a finite box without breaking supersymmetry and without breaking rotational symmetry. So it's a funny box, which is rotationally invariant.
Sorry, could I ask, in relation to your initial motivation with gravity?
So my theory now with finite epsilons is a quantization. It's a quantization of some the classical geometry, which is given by the limit sheaf.
There is no reparameterization.
It's all gauge fixed. So so you can say there is actually a way of formulating this theory in which the preferred coordinate. I mean, so gauge theory gives a preferred coordinate as in matrix models actually, which is the coordinate in which the eigenvalues of the Higgs field are measured. You can introduce a redundant variable, which will be a reparameterization of that coordinate. So this corresponds to introducing the higher times into the problem. But in the simplest form, when this gauge is fixed, this is what you get.
Topology is always clear.
Because this is one-dimensional geometry, so what can you expect from?
You mentioned like two-dimensionality.
Well, we'll get there. We'll get there. I'm just saying that. So we are getting acquainted with building blocks, out of which I will be building more complicated structures. So you see, this is the step one in the sequence of possibilities. So the four-dimensional gauge theory gives that structure. It's one-dimensional, but already this one real-dimensional geometry actually hides complex analytic curves. So the whole, so these simple-looking geometries are actually governed by the families of Seiberg-Witten curves, which are already non-trivial. Topology in this case is not the right word. So the complex structure is emerging out of these considerations. The topology is really fixed by the rank of gauge group, the number of colors. That's the only parameter. Now, if you try to generalize this story to high-dimensional theories, which of course do not make sense as quantum field theories, because they're not renormalizable, you can make sense out of them by embedding them in string theory. So by viewing them, for example, as theories on stacks of D branes in type 2A or type 2B theory in various backgrounds. The quantity which we are trying to compute will be, again, the supersymmetric partition function. So the massive states which we introduce in embedding the theory to string theory will not contribute. And nevertheless, these computations, even though they don't capture the ultraviolet behavior of string theory completion, they will help us to confirm or test some of the most remarkable predictions of, let's say, 20 years ago, 25 years ago, that in doing the summation of a D0 brane contributions in type 2A string theory, you recover high-dimensional theory. You will live to 11 dimensions from type 2A, or maybe even higher. So the simplest example of that computation is a slight upgrade of what I discussed so far. It's the partition function of a 4+1 dimensional theory, compactified on R4 cross S1. So the partition function you can interpret in the Hamiltonian fashion as the trace of the Hilbert space obtained by quantizing the theory on R4. We insert -1 to the fermion number, so it's a Witten index. But we also insert certain global symmetry elements into this trace so as to make it slightly non-trivial. So it will depend on the parameters which will probe the symmetry structures of the vacua of that theory. And so the parameters which we have at our disposal are two angles of rotations of R4, again, which here I will parameterize in the multiplicative form, in the exponentiated form. The chemical potential for the number of instantons, or D0 branes in type 2A string picture, the fugacity for the number of instantons, I call it P. And another parameter, the chemical potential for the flavor symmetry, which in four-dimensional terms would be the mass of the adjoint hypermultiplet. So the theory which I'm studying here is the maximally supersymmetric Yang-Mills theory uplifted to 5 dimensions. So in 4 dimensions, the theory has a deformation which preserves n equals 2 supersymmetry, which gives a mass to the adjoint hypermultiplet. In 5 dimensions, you can make this deformation by turning on the Wilson loop for the flavor symmetry. And so again, the partition function of the theory, in the simplest case of U1 theory, can be computed. It is again the sum of the partitions of Young diagrams. The contribution of each Young diagram is a slight modification of a Plancherel measure, which depends now on all these parameters. And remarkably, the partition function can be resummed into the form of the so-called platistic exponent. So it's an expression of the form. You have some basic function, which is actually has a meaning of a trace of a single particle Hilbert space of some symmetry group, and then the full partition function is that of a Fock space built on the single particle space. So the single particle partition function, you should expand this in the sum of the monomials, and so you actually in general will get plus and minus terms. So plus terms will correspond to elementary bosons, and minus terms will correspond to fermions, and so you get bosonic fermionic multi-particle states, which I accounted for by this platistic formula. And now the miracle is that that very function, even though we got it in doing the 4 + 1 dimensional computation, coincides with the partition function of a tensor multiplet of a 6-dimensional 0,2 supersymmetric theory compactified on the 6-dimensional spacetime of the form R4 fibered over a 2-dimensional torus. And now the fugacity for the number of the zero branes, or for the number of instantons, becomes the complex modulus of this torus. Remarkably, so that's the 0-2 theory in 6 dimensions is believed to be a superconformal theory, for which in general we don't have a Lagrangian. Now the conformal theory, once you compactify it on the space, on the geometry which has some scale, should not depend on the overall scale. So if I compactify it on the space of the form, the product of R4 cross T2, the partition function of conformal theory should not depend on the overall size of the T2, but it will depend on the ratio of the sizes of two circles, or more generally on the complex structure of the torus. And indeed it depends on it. Remarkably, it depends on it in a holomorphic way. That's the consequence of supersymmetry.
So what's the starting point for this calculation?
So the starting point was the computation of the 4 + 1 dimensional partition function. So there you start with Lagrangian, you take the super-Yang-Mills Lagrangian, you now view the 4-dimensional Yang-Mills action as the energy, not as an action, but as an energy. So that now the minima of that functional, which are instantons from the 4-dimensional point of view, will be described solitonic particles in 4 + 1 dimensional theory. So the solitonic particles will go around the circle, which is the circle of my trace, and taking into account the contribution, produces some formula. So there, the tricky part is that these instantons, they form bound states. So you can have a solitonic particle, which is a genuine bound state of 5 instantons, but in the same partition function, you have a contribution of 5 separated instantons going around the loop. So all of these are incorporated in this partition function. Yes?
This exponentiation is just a consequence of localization, that it's effectively one determinant.
No, this is a consequence of the fact that in the U1 case, the lift to 6 dimensions produces a free theory. It's a free tensor multiplet. If I had I started with the let's say SU2 gauge theory in 4 + 1 dimensions, then the 6-dimensional theory would be interacting theory, and then this partition function will be much more complicated. It will not have this platistic form. It will have corrections which will contain the contributions of genuine bound states of 2, 3, and so on.
But
so
there could be also solitons which have non-trivial time dependence.
They will not be preserved by the supersymmetry of that partition function. So they will not contribute to that computation. Like if you think about something like dions, dionic particles, well, dionic particles are actually accounted for, but for them the time dependence is is simple. It's a constant velocity motion on the electric circle. So those are accounted for in this partition function.
But this is one of the loops in 6 dimensional
Well, you know already. So already in that theory, so if this model is a limit of it's a limit of the 5-dimensional problem. So you know that already in that theory, by exploring the periods of the Seiberg-Witten curve, you will see the contribution of monopoles becoming massless at certain points. And so the loops of those monopoles, which determine the shape of this limiting geometry, are already in this partition function. So you don't include them. You don't separately include them. They are already included in this computation. So the computation is done in so-called electric frame. But if you do some kind of Fourier transform, you can probably see them in the naked eye. Okay, so now let's do now a more interesting case where instead of summing over 2-dimensional partitions, we now, instead of building geometries out of squares, let's build geometries out of cubes. And so that turns out to be the correct enumeration of instantons in the 6+1 dimensional theory, which now is the theory on a D6 brane in type 2A string theory. Now, in type 2A string theory, in flat space, D0 branes do not bind to D6 brane. They don't form a supersymmetric bound state. However, if you turn on a B field, the Schwarz B field, the supersymmetric conditions change, and the effective potential between the 0 brane and the 6 brane also changes sign, and so they start binding. Another way to see that is that the gauge theory on the D6 brane wall volume becomes non-commutative. So in that, here it's a space non-commutativity. It's not the space-time non-commutativity, which I think was taking place in Sasha's talk. So it's a more conventional type of non-commutativity. And so that, again, even Maxwell theory on non-commutative space will support instantonic particles. And so you can set up the problem of calculating the twisted Witten index for that theory, which now will depend on 3 angles of rotation, because in 6 dimensions you have 3 independent rotational planes. And remarkably, the partition function again has a platistic form, where now this free energy depends on 3 rotation parameters and 1 fugacity of the 0 branes. I mean, again, it's in the previous case, we also had 4 parameters, but there 2 had the meaning of rotations along the space-time of the theory, and 1 had the meaning of rotation of the transverse space. So here, all 3 angles are angles of rotation of the 6-dimensional space. There's also an accompanying rotation of the transverse space, which is needed to preserve supersymmetry, but that's determined by these angles. And now, when you explore this formula for the free energy, by slight massaging of the formula, you discover that the symmetry of that formula is actually higher than what you could have expected. So just the fact that you had the 6+1 dimensional theory meant that there should be a symmetry which permutes 3 angles of rotation, because that's just part of the Weil symmetry of the rotation group. But the final answer enjoys the permutation group of 5 elements, which permutes the geometric parameters, the rotation angles, with the fugacity for the number of instantons. And so that's a kind of a strong weak coupling symmetry, which is completely unexpected from the point of view of the combinatorial model of summing over 3-dimensional partitions. Now, I should tell you historically, so this picture, the way it's written, it's, of course, your eye recognizes this as a 3-dimensional picture, but you can also view it as a purely 2-dimensional tessellation of a 2-dimensional plane by 3 types of rhombi: yellow, kind of purple, and blue, which have 3 prescribed orientations. And so this is the particular configuration is what is known as a dimer model. So these configurations of rhombi is what you can draw on a hexagonal lattice. And so these models were studied in statistical physics a long time ago. The novelty of the supersymmetric gauge theory is that the statistical weight of this model depends on additional energy imposed on these Romberg configurations. So the remarkable thing is that that partition function actually coincides with Witten index of 11-dimensional supergravity. So these 5 parameters which you cook up out of 3 rotation angles and the fugacity, the 5 parameters whose product is equal to 1, so they're not independent, happen to be the rotation angles of a rotation of a 10-dimensional space in the background of 11-dimensional supergravity, where you fiber 10-dimensional space over a circle with a twist. And now this twist, if you choose this twist to be in SU5, not the general spin 10 twist, but a special twist, it will actually preserve some of the global supersymmetry. And so in that context, you can set up, again, a Witten index type computation. Even though in supergravity theory, normally you would not consider rotations as global symmetry, here we're doing computation in the background, which is non-compact. And so this non-compact background has asymptotic symmetry. And so we use that symmetry as a parameter in partition function. And so if you just enumerate the fields of 11-dimensional supergravity, take all the modes, all partial waves of gravitons, Arita-Schwinger field, the 3-form field, organize them in multiplets of rotation group, and then decompose them with respect to the SU5 subgroup of rotation group, that's the partition function that you will get.
Technically, it's just one loop computation with the background, which is
Yes. But what's interesting is that that computation was done in type 2A string theory. So this was a 6+1 dimensional gauge theory, from which you can also cast as a computation in string theory when you only take into account the ground states of open strings stretched between 6 branes, D6 and D0 branes. But the result can be reproduced by doing the one-loop computation in 11 dimensions. And so that's a confirmation of the duality between 11-dimensional M theory and type 2A string theory. So that was a story of some number of years ago. So that formula was a conjecture I put forward in 2004. And A.Okounkov, mathematician, proved it rigorously now 3 years ago. So that's a theorem. Mathematically, it's a theorem. And so the proof was that that the sum of the 3-dimensional Young diagrams, which are the configurations of this form, which depend on the 3 rotation angles and the fugacity parameter. So I didn't give you the formula for the measure. It is some interaction. It's a Boltzmann weight of some interaction potential between pairs of corners of this diagram. So that measure is a one-loop computation in supersymmetric gauge theory in 6+1 dimensions. And so that sums up to this Platistic exponent with this formula for the free energy. So that it is indeed has the free field form. So that's a theorem.
So this measure is different from the number of ways to build?
Yes, it's a more complicated measure. It depends on the geometry. It depends on the geometry on the 3-dimensional shape of the diagram. So these 3 parameters, they roughly scale. They measure. They treat the 3 axes in a different way. So by playing with these parameters, you can make your diagram, prefer being more flat in one of the planes. If the product is equal to 1, then it becomes a uniform measure. It's not a Plancherel measure; it's a uniform measure. So this is the special feature of 3-dimensional Young diagrams. The natural measure on 3-dimensional Young diagrams is just count all of them on equal footing, only paying attention to the number of boxes. So that's the simplest measure. It is related to the Plancherel measure in 2 dimensions. If you sum over all 3-dimensional diagrams whose 2-dimensional shadow fits within a given 2-dimensional Young diagrams, you will get the Q analog of the Plancherel measure. Now, so for a long time, since 11-dimensional supergravity is maximal supersymmetric field theory, which one can have by Numm's theorem, for a long time I thought that the only meaningful problem with counting boxes would be a 3-dimensional problem. And also again, A.Okounkov, my colleague and friend, always told me that whatever you do with crystals, so this is also the model of a melting crystal, if you can recognize it. So whatever you do with crystals, you don't generalize it to 4 dimensions. So it's a bad mathematical problem. And there is there's some history of that, which I will review later. So for a long time, I thought that that was the case. But then for no good reason, maybe 3 years ago, I started playing with 4-dimensional Young diagrams, so build structures out of hypercubes. And it turns out that you actually get nice formulas. So there is something beyond the story which I just described. And so one actually set up a count of solid partitions. Solid partitions are the 4-dimensional Young diagrams. The first question you need to address is how to visualize them. So you visualize them just the way you visualize the 3-dimensional Young diagrams. You project 4 dimensions down to 3 dimensions along the principal axis. So in 3 dimensions, we take the 3-dimensional space and project it along the principal diagonal. And so that way, the cube projects into the collection of 3 rhombi. So you have 3 orientations. And if you place this rhombi this way, you see the cube which sticks out. If you actually place the rhombi this way, then you remove a cube. So that's a way to visualize the modification of 3-dimensional Young diagrams and building geometries. Now, analogously, you can do with 4-dimensional structures. You'll project them to the 3-dimensional space. And what you will see instead of this 3 rhombi picture, you will actually see 4 cubes, 4 squashed cubes with interesting geometry, which I will not talk about, except that the angle between 2 edges of such a cube has cosine which is equal to -1/3, which is a new constant of nature. So for the ordinary, if you do it from projection from 3 to 2 dimensions, the cosine of this angle is -1/2, and that angle we know, it's 120 degrees. But when doing projection from 4 to 3, the cosine is -1/3, and that's a new number. Anyway, one day I will have somebody printing out on a 3D printer these cubes and forming a tessellation of a 3-dimensional space. Well, of course, not the full space, otherwise we will not be able to breathe, but just to see, to get a feeling for these structures. So that's the now random 3-dimensional geometry, which you get by building a simple structure in 4 dimensions and then projecting. For those of you who heard about quasicrystals, that should remind you the old idea of Levitov, Kalugin, and Kitaev interpreting quasicrystals in our space as a projection of crystals from high-dimensional spaces. So there's something like that going on here. So that's the picture of the geometries. And now, in the remaining time, let me just tell you a little bit of history. In 1916, thank you, Major McMahon, Percy McMahon, who was the president of London Mathematical Society, was counting partitions. So that was a respectable mathematical problem. So in the ordinary partitions were actually counted for by Leonhard Euler a long time ago. And the generating function for the number of partitions of a given size, you can compute. It's very simple computation. That's a free boson in 2 dimensions. Now, McMahon started by counting partitions in 3 dimensions, and he actually announced a formula which he didn't prove, that the generating function of the number of 3-dimensional partitions also has a simple product form. Now these factors have an additional power n. he didn't know that you can actually recognize it as a partition function of a conformally coupled scalar on S1 cross S2. So it's a three-dimensional scalar theory. That formula is true. It was proven rigorously in the 60s. And so the partition function, which I was talking about, is a generalization of that partition function. Now, McMahon actually generalized this formula for the four-dimensional partitions. So he thought that the structure is that here the exponent was 1, here it's n, so that should be the next binomial coefficient. And if you were a physicist, you would have actually checked this formula in the first 5 cases, and it was actually gives the right answer. So the first 5 numbers are precisely correct. At the number 6, it gives 141 instead of 140. So it's less than 1% error. In fact, even for 16, it gives 217,000 instead of 214,000, which is a very small mistake.
By numbers, you mean what?
So this is the actual number of four-dimensional partitions, and this is the expansion coefficients of that function. And nowadays, people do actually computations on supercomputers and do it for hundreds, the partitions of a size of hundreds, when numbers are enormous, and his formula still is pretty accurate, but wrong. And 100 years later, the formula is not known. But now, the supersymmetric gauge theory assigns a different measure to these four-dimensional partitions. So it actually cares about the shape of the partition, not just the size. And so the formula which I got by doing just experiments, again, has a statistic form with now more parameters, and has a generalization to several colors. And so that formula was checked with by myself and my postdoc Nikita A.Okounkov for up to 16 instantons. So that's an important number. So that's that many cases. So it's beyond what McMahon checked. And Rubik Pogasyan told me that he actually even managed to push it even for 17. So the formula must be right. There's no physical formula which is true for the first 17 cases and then false. Cannot be.
So it means it's exact? Or?
It's not proven. It's not proven, but it's
I understand, but when you are checking to come,
yes, it's exact. Yes, up to.
you are getting the same numbers?
Yes. No, so this is how many terms you need to sum over
Okay, very good.
to get this formula. And so what's it?
But to what extent it's correct? I mean, can you...
So gauge theory tells me that for each four-dimensional partition, I assign a certain rational function of these parameters q1, q2, q3, q4, and so on. So it's some huge expression. Then I sum over all these partitions and simplify, take a logarithm, and this is what I get. And so this is true to to this precision. Yes. So to this case.
Can you extract number of partitions from that?
Probably not. I mean, it would be interesting. So there is no simple way to specify these parameters to make the measure uniform. If it were the case, it would be remarkable, but most likely not, because what these people discover, this is for some reason these people in India do that on supercomputers, is that asymptotically McMahon formula is very precise. And the growth of my formula is that of the three-dimensional McMahon formula, not of that of four-dimensional McMahon formula. So it's less.
You try to take q to 0.
Yes. Okay. So all tests, it passes all the tests, and the question is, what's the theory beyond 11 dimensions whose partition function is given by this free energy? Thank you. If there are no questions, I just tell you a little story. So to check this, so I'm not an expert in numeric computations. So to test this formula, I had to set up a parallel computing. So I took 7 laptops. So some of them were very old, and just wrote some simple code, and then had these laptops do computations, then feed the results of the computations in themselves. And then, after doing this for maybe a week or so, I realized that I'm sitting in my office with 7 laptops, and this is like history repeating itself, but again, as a farce. So in the 50s, when there were no computers, or maybe in the 40s, and people were doing numerically estimating the rate of nuclear reactions for the important project, the way people were computing this by human computers. So there were 50 girls who were given blocks of some computation, which were doing computations by hand on a arithmometer, and then feeding these computations to the next girl. And there was one Landau who was supervising this whole enterprise. And now, 50 years later, that's what the world came to.